Hi Chem 240, this is Dr. Ricardo. This is the second video for the electrochemistry chapter, which is chapter 20. So, first thing we're going to do, actually the only thing we're going to do in this video is practice balancing redox equations. And the method that we're going to use is called the charge before mass method. The other method that's used is the mass before charge method. So it's basically the same, but I've been kind of doing it this way for a while, and I personally think it's easier. So here's what you do. The first thing that you have to do is you have to split the skeletal equation that they give you. So they're going to give you an equation that's going to have a lot of O's and H's especially missing. Waters and H pluses for acid, and OH minus if it's in basic solution. So they're going to tell you it's in basic solution or it's in acid solution. So the only thing that's really going to be in the equation that they give you are the pieces that are oxidized and the pieces that are reduced, okay? And they're going to say this particular one is in acid or this particular one is in base. So the first thing that you have to do is you have to split the skeletal equation, which is what they give you, apart into the two half reactions. So what does that mean? Separate all of the items that are being oxidized, the reactant and the product that's being oxidized, and the reactant and the product that's being reduced into two half reactions. The next thing that you do is you balance the number of atoms of each element other than hydrogen and oxygen on each side. So for instance, if you're looking at one that has two chlorine atoms on one side and only one on the other side, then the side that only has one, you have to obviously multiply by 2. So make sure anything other than hydrogens and oxygens, which are kind of like our extra pieces that we're going to put on at the end, make sure that those elements are balanced. So you can't have two magnesiums on one side and only one on the other side. You've got to balance that. Second thing, balance the number of electrons either lost or gained in the half reactions by the oxidized or reduced species. So you need to come up and figure out what's oxidized, what's its original oxidation number, what's its final oxidation number, and put the electrons on whichever side you need to so that those charges balance out. So this is the charge before mass method because we're taking care of the charges right away. And you've seen us do that in the last section where we saw something like copper plus 2 on one side and then copper solid on the other. So we quickly added 2 electrons to the reactant side because copper plus 2 captures 2 electrons to go to copper solid. So it's mostly looking at the oxidation states of the species that are oxidized and reduced and putting the electrons where they're needed. Okay, so you have to do that to the oxidation side and the reduction side. Don't worry that you may have a 5 electron oxidation and a 3 electron reduction. We'll take care of that later. The next thing that you do is depending on if you're an acidic or basic solution, and in the question they're going to say this is done in acidic solution or this is done in basic solution. So you do this one if it's acidic, you do this one if it's basic. In acidic solution, you balance the charge in each half reaction by adding H pluses to the more negative side. So after you add the electrons, then you add H pluses to the more negative side. Okay? If it's in basic solution, you balance the charge in each half reaction by adding OH minuses to the more positive side. So the tool that you're using to get the charges right are H pluses to balance off the electrons that you added, or OH minuses to balance off the electrons that you added. And you're just going to put them on one side or the other. The next thing you're going to do is you're going to balance the H atoms by adding water to the opposite side. So if I have one side that's more negative than the other and I have to add 6 H pluses to one side, well now all of a sudden I've got too many H's on this side. What about the other side? Well, I'm going to add 3 waters to the other side. Same thing over here. If I have to balance the charge, like one side is way too positive, so I have to balance that by putting hydroxides on that side, and I put 4 hydroxides, then wait, I'm going to have way too many H's. So what do I have to do? I have to put 2 waters on the other side. So after you balance the charge by using the negativeness and the positiveness here, then you're going to balance the number of H atoms on either side. Okay, so you take care of H first. And then what's going to happen is, if all went well, you did everything right, the oxygens should have taken care of themselves. They should already be balanced. The next thing you do is check the mass balance and charge balance on each half reaction so that each half reaction is totally complete. The total charge on the left-hand side of the half reaction is equal to the total charge on the right-hand side of the half reaction. This is with the electrons still in it. And the number of each kind of atom in the half reaction are the same on the left as they are on the right. Okay, so that part over here, the only part that depended on acid or base was this C1 or C2. You go this way if it's acid, you go this way it's base. Okay, D's the same for both, E's the same for both, F's the same for both, and 3 and 4 are going to be the same for both too. Okay, next thing that you do is now you have two perfectly complete half reactions that have all the parts, but one of them may be a 3-electron oxidation while the other one is a 6-electron reduction. Well, the next thing you need to do is multiply each half reaction by a factor such that when the half reactions are added together in the balanced equations, all the electrons cancel out. So if one of them is a 3-electron oxidation and the other one is a 6-electron reduction, you have to take the oxidation and multiply by 2 because the total number of electrons that are passed from one thing to another has to cancel out. Okay? After that, you have two half reactions. All of the electrons cancel out. You combine the half reactions, cancel the species that occur on both sides of the equation. Obviously, all the electrons have to cancel out, but a lot of times you're going to have H pluses, OH minuses, and waters that are going to cancel out on both sides, especially when the oxidation reaction and the reduction reaction are both with oxyanions. Then you're going to have a whole lot of extra waters on both sides and you're going to cancel them out. So that's step 5, that's simplifying. And the last thing you want to do if you have enough time is check again, right? You check that up here that both the half reactions were totally balanced. Well, you also want to check at the very end that the mass balance and charge balance on the overall final answer is also balanced. So here's our first example, okay? And this is the way you're going to see it. You're going to see Br minus aqueous plus, so this is a bromide plus permanganate goes to bromine and magnesium plus 2. So all of these 3 species are aqueous. I just didn't write it down because it's going to be a lot of writing. And the bromine is going to be in the liquid state. And the last thing I tell you is this is done in acidic solution. Okay, so I have to separate up here what's oxidized from what's reduced. It doesn't matter which one you put on the left and which one you put on the right, but it's kind of nice to work in parallel. So you can make a line down the middle of your page, do the oxidation on this side, the reduction on this side, and then you're going to put them back together. So you won't forget to put them back together if you have them right in front of you. Okay, not a bad idea to turn the paper sideways when you do these, and I think I did that in the future ones. Okay, this was a pretty short one, so I didn't have to do that. Okay, so I look up here and I see what's the oxidation state on Br minus 1? Well, it's minus 1. The oxidation state on a monoatomic ion is the charge on the ion. What's it in bromine here? It's 0. So what's happening to bromine is bromine must be losing electrons. Each bromine is going from minus 1 over to 0. So that's the oxidation. Oxidation is the loss of electrons. So I write that over here. I write these two things first. That's what I would have. And then the first step is to balance the number of atoms. Well, I can't have 2 bromines on the right and only 1 bromine on the left, so I add that too. Then the next thing I have to do is add the electrons. Add the electrons that you see are either lost or gained. Well, if I have 2 things at minus 1 and both of them go to 0, then what had to happen is each bromine lost an electron, so that's a total of 2, and they hooked up, they got together to make a covalent bond between them. So first they're 2 individual bromide ions with a -1 charge. Then they lose 2 electrons, okay? They lose 2 electrons and they get together to make a bromine-bromine single bond. Okay, now I'm done with this one because there's no H's or O's in it, so I don't have to worry about anything else. And the very next step would have been balance the charge, but check it out. The charge is already balanced. 2 times -1 equals 2 times -1, and this guy's equal to 0. So that's called the charge balance. I would only have to add H's, H pluses to one side and waters to the other, if these numbers didn't naturally come out to be balanced out. That's what's going to happen in the next one. The next one, you're going to have to go through the whole rigmarole. I could tell this was going to be an easy one because it doesn't have any extra O's on it like this. Okay, look at this next one. When we do the reduction, this is going to go from something that's got 4 oxygens on it to something that has no oxygens on it. So I'm going to have to be adding oxygen somehow. So that's coming over here. Okay, let's take a look at what's happening in reduction. Why does this piece come over here? Because the manganese is going from the +7 state over here to the +2 state over here. Okay, make this a little bit bigger. Okay, it's going from +7 to +2. The charge on a monoatomic ion is the charge. And why is this +7? The whole thing is -1. And then 4 oxygens in the oxide form, each at -2 gives you -8. So the manganese has to be +7. Okay, so first thing we write down is we write down the 2 parts over here. I realize it's reduction because, look, I'm going from +7 to +2. That's going to have to gain 2 electrons to go all the way from +7, right, to +2. This thing is losing 7 electrons. I need to give it 7 electrons to bring it back to +2. Don't worry about the O's yet. Don't worry about the negative sign. You're putting these electrons just to balance, take care of the electrons that are lost. There's only one Mn, so that's okay. So that's the next step. The charge before mass method is add the number of electrons needed to take care of the fact that the manganese moved from +7 to +2. All right, when I get after that step, what's the next step? I need to add, we're going to do this in acid, right? So I need to add H pluses. To whichever side is more negative. So look at this. This is a very negative side. This side has a -1. I'm talking not about the oxidation states. I'm talking about the overall charge. This has a -1 and a -5. The whole thing over here is -6. Whereas over here, this guy is +2, right? Look at that, +2. So I have to add H pluses because it's acid. So how am I going to get something that's -6 all the way up to +2? I think I'm going to need to add +8 H pluses, right? Because +8 H pluses will take care of that -6, and I'll get a +2. So that's the next step, is add those 8 H pluses. Okay, the next step after I add the 8 H pluses is I have to balance the H atoms by adding water to the other side. Look, there's no other H's here. There's no other H's here. So I'm going to need 4 waters on the other side. Okay. Last thing you do is make sure that the oxygens should have fixed themselves if you did it right. And that's true. There's 4 O's here and there's 4 O's here. So everything is balanced. Then check that the charge balance is okay. Well, that should still be okay because the last step was just adding water, which doesn't change anything. So this whole side is +2. This whole side is +2. All right, now I'm going to put together my 2 parts. So take a look at those 2 parts, right? There they are. This one, I'm going to make it a little smaller now. This is a 10 electron, this up here is a 2 electron oxidation. This is a 5 electron reduction. Can't put those 2 together. I have to multiply this guy, leave this, the only place that 5 and 2 get together are 10, right? If I told you I had to add 1/5 and 1/2, you've got to multiply by the 1/5 by 2 to make them 1/10 in the denominator, and you have to take the 1/2 and multiply them by 5 to make them 1/10. And then you can add tenths up. The denominators have to be the same. So this guy has got to get multiplied by 5, and this guy's got to get multiplied by 2. Okay? I think the best way to sort is kind of the least common denominator. So if I multiply this whole reaction by 5, this guy goes to 10, this guy goes to 5, and 2 times 5 gives you 10. If I multiply this one over here by 2, this goes to 16, this goes to 2, 5 times 2 is 10, 1 times 2 is 2, 4 times 2 is 8. Now, put them together, rewrite them in the middle, because we're putting them together. So all this is just me rewriting this, and me rewriting this one. And I see the 10 electrons that were oxidized are canceled with the 10 electrons that were reduced, and I get my final answer. There's nothing else that cancels here, and I can tell you why that happened. It was because the top one was a super simple one that had no oxygens or hydrogens in it that were dangling around, that were extra, okay? That's my overall answer. I can check it out. The charges balance, because this whole side is equal to a +4. Check it out. +16 and a -10, right? Well, let's do the minuses first. This is a -10 and a -2 gives me a -12. And here's my +16. So this whole left-hand side equals a +4. So the whole right-hand side has to equal to +4. This is 0. 5 times 0, and this is 8 times 0. So the only charge over here is 4 times +2 gives me +4. So it has to be the case that +4 equals to +4. That's called the charge balance. You can't create or destroy electric charge in chemistry. Okay, next thing, check all of the atoms. I'm not going to do that, but the H's should balance, the total H's, okay? The total MNs should balance, the total BRs should balance, and the total O's should balance. Okay, so that was the first example. It was done in acidic solution. This is what you're going to get. You're not going to get a lot of information. You're just going to get that very small amount of information. Just going to erase this so I go back to what I started with. And what was up there is the oxidation state of manganese in this species, +7. Okay, so those are the numbers I'm originally working with, the oxidation states. Don't confuse them with the overall charge on the ions which are given to you. Okay, here's another example. So this one says zinc plus nitric acid goes to zinc nitrate and ammonium nitrate. So this is given to you. It's going to say over here in acidic solution, okay? It's going to say in acidic solution. I'm sorry I didn't write that, so maybe I can put it over here. In acidic solution. Okay. All right, so let's see what's oxidized and then let's see what's reduced. Okay. What's happening to zinc? Zinc is going from zinc in the 0 state because it's an element to zinc in the +2 state. We know the nitrate ions are -2, so if I reverse crisscross this guy, zinc was in the +2 state. Okay? Nitrogen is participating in this chemical reaction, so something's happening to nitrogen as well. Okay? So the first thing I might say to myself is break this out into its ions. Zinc nitrate is very soluble. All nitrates are soluble. So you probably want to rewrite this as zinc +2 and 2 NO3 minuses. Okay? And then you can see that what's happening is you're starting with this nitrogen over here, and it's going to break up into nitrate and ammonia over here. Okay, so this is, let's take care of the oxidation reaction. That's super simple, right? What's happening on oxidation side? Zinc is going from zinc in the 0 state to zinc in the +2 state. So this is just a spectator ion over here. This guy's not doing anything. It's this guy over here that's going to be changing dramatically from nitrogen in nitric acid to nitrogen and ammonia. This guy here, the extra nitrates, are going to be just the spectator ions. This one and this one aren't really going to, excuse me, this one and these ones aren't going to do anything. That's where the magic is happening. Okay? All right, so let's do this zinc first part, okay? So zinc is going from zinc to zinc +2. All right, so that's an oxidation, so I realized that right away. So the first step is to balance any elements other than hydrogen and oxygen. Well, there's only one zinc, so there's only one zinc, so leave it alone. Next, add the number of electrons needed to take care of the fact that the electrons, that you lost 2 electrons, okay? So there's the 2 electrons. So zinc goes to zinc +2 electrons. I'm done with this part. This is one of those simple ones. There's no extra oxygens or hydrogens, so there's nothing else to do. That has charge balance and mass balance, so don't overdo it. One zinc, this total charge here, 0 equals 0. +2 and -2 equals 0, okay? Leave that one alone. come over here, work on this guy. Okay, so first thing I realize when I'm up here is let's calculate the oxidation state on nitrogen in nitric acid. So oxygen is -1, and there's 3 of them, so this guy makes it -6. Hydrogen is +1, so what must nitrogen be? It must be in the +5 state, okay? All right, come over here. Change dramatically, right? Over here, in ammonia, what happened to nitrogen? Hydrogen is always in the +1 state, so this guy is +4. The whole ammonium ion, NH4, is +1, right? So if each hydrogen is +1, that gives me a total of +4 over here. What must the nitrogen be in? It's in the -3 state. So nitrogen is going from the +5 state to the -3 state. Okay, so the first thing that you redo is rewrite the nitric acid part down, right? And rewrite the ammonium nitrate down. Okay, don't worry about this part over here. This is the part that's undergoing the change. This part is +3 over here. +5 over here. This is still +5, so this is just a spectator ion. So it's not going to do anything. Really, we're watching this go to that. Okay, first step, count up the, I add this 2 here to take care of the fact that this nitrogen over here, there's only 1 nitrogen here where there's 2 over here. Okay, next step, nitrogen is going from the +5 state to the -3 state. One of the nitrogens is going from +5 to -3. So how many electrons do I have to add to go from +5 to -3? Well, I have to add 5 to get to 0, and then 3 more to get to -3. So that's why this is an 8 electron reduction. It's a reduction because the electrons are used up. Okay, next thing, the other nitrogen didn't change, so I don't add any electrons. It stays at +5. So these 8 electrons are there to take care of the nitrogen that's turning into ammonia. All right, let's make sure that this has charge balance and mass balance at this point, okay? So when I look at it, what's the whole charge? Forget about the oxidation states now. The whole charge on the right-hand side is 0. The whole charge on the left-hand side is +8. So I have to add 8 hydrogens on this side, 8 H pluses because it's an acidic solution, to balance this negative charge. So that's my motivation for putting those 8 hydrogens. 8 hydrogens, the 8 pluses balance the 8 minuses. This is 0 to equal 0 on the other side. Okay, what's the next step? I need to add waters to the other side. I need to add waters to whichever side to balance the hydrogens. So there's 2 hydrogens here plus 8 hydrogens here. That's 10 hydrogens, right? So how many waters do I need? I have 2 here and 8 here, right? That's 10. I've got 4 here. Don't forget those 4. So how many more do I need? I need 6 more over here. So if I'm dealing with waters, I have to add 3 waters. So these 6 H's plus those 4 H's equal these 2 and those 8. There's 10 H's on each side. Now, last step. If you did it right and the charges are balanced and the hydrogens are balanced and all the other elements are balanced, the oxygen should fix themselves. So how many oxygens do I have? 2 times 3 equals 6. Here's 3. And there's another 3. So there's 6 oxygens on each side. So this guy is totally balanced. This was hard. This was hard because this is distracting. You're not going to usually have something like that in there. You're going to be just taking care of something that would be more realistic if I just made you go from that guy to that guy. Okay, but it all worked out. Okay, last step. Let's compare the left-hand side and the right-hand side. It's time to put them together. This is a totally balanced half reaction in acidic solution. This one would be a totally balanced half reaction in any solution. This is a totally balanced half reaction in acidic solution. So this is an 8 electron reduction. This is an 8 electron oxidation, so leave them alone, right? They just happen to work out perfectly. I don't have to multiply this side by anything to match it up with the other one. They're already matched up. These 8 electrons are going to cancel with these 8 electrons. So what do? I take them from their 2 columns and I put them one underneath the other on the table. Okay? So rewrite, doesn't matter which one you put on top. I put the oxidation on top. Didn't do anything to it. Put the reduction underneath. Cancel anything out that's on both sides. So my 8 electrons has to cancel. Nothing else cancels. I'm already sure of that because this first one was one of those simple ones. Okay? So if I do that, I wind up with 4 zincs, 2 nitric acids, plus 8 hydrogens in acidic solution, make 4 zinc plus 2s, plus ammonium nitrate, plus 1 ammonium nitrate, plus 3 waters. Everything else canceled out. To see this reaction in basic solution, so this guy is totally done. Then what you can go back and put in the spectator ions, right? The spectator ions are, you can add, in chemistry, as long as you do the same thing to the left-hand side and the right-hand side, you can get these things with all of the nitrates on it. So these 8 hydrogens, you can put 8 nitrates on there. These here, these 4 zinc plus 2s, you can put 8 nitrates on there to make it 4 zinc NO3 2s. And that's when you'll see everything with all the nitrates. Or you can sort of leave them off because, again, these are just spectator ions. Those nitrates aren't doing anything. Okay, I'll just rewrite it with the nitrates so you can see what I mean. Okay, if you wanted to see these with all the nitrates on there, this guy would be in solution. You have to have a counter ion, so these guys would be totally filled up with nitrates. So this would, instead of writing 8 H pluses, I would write H, H, and O3s, right? And then over here, on this side, instead of writing 4 zinc plus 2s, I'd write 4 ZnO2, like that. So there's my 8 extra nitrates. So this would replace this would stay the same, this would stay the same, this would stay the same, this would stay the same. It's just, you get the same thing. Okay, remember those nitrates aren't doing anything but watching. Okay. Okay, if you had to do this in basic solution, one of the ways that some people do it is instead of doing a basic solution right from the beginning, is they turn around and they just neutralize all of the H pluses. The oxidation reduction part of this is over. You could go back to Chem 1 and you can just neutralize all the H pluses with OH minuses. So basically what you do is add the same number of OH minuses to both sides of the equation, but what will happen is on the H plus side, the side with the extra A pluses, they're going to instantly form waters, right? Because H plus and OH minus makes water. So you're going to get all these extra waters that will cancel out with some of the waters on the other side, and you'll wind up with the correct answer as though it was in basic solution. So one strategy is do them all in acid, and at the end, if I ask for it in base, just neutralize the H pluses with OH minuses. So let's go ahead and do that. Before I added these hydroxides here, I had my 8 H pluses. So if I want to do it in base, I add as many OH minuses to the other side, to both sides, to neutralize all the acids. So I purposefully add 8 hydroxides here. Well, whatever you do to the left, you got to do to the right. So if I add 8 here, I've got to add 8 here. Okay? Those 8 H pluses and 8 OH minuses are going to cancel out with each other to make 8 water molecules. Okay? Now, you have 8 water molecules on this side and 3 on the other. So all 3 of these cancel out, and 3 out of the 8 cancel out, leaving you with 5. So this will be balanced with 5 hydroxides on this side and and 3 waters on this side. Okay? Oops, sorry. All 3 of these waters cancel out. So it would have, 8 hydroxides on this side. Those canceled, right? And then of these 8, 3 of them canceled out, so there'll be 5 left. So take a look at this. This is totally balanced in base. How do you know that? Because the excesses are hydroxide. Up here, it's balanced in acid because you've got H pluses around. So H pluses will either be a reactant or a product, but there'll be no OHs because there's no OHs that exist in acidic solution. And down here, hydrogen ions don't really exist in basic solution. Hydroxide ions exist. But let's make sure this is totally balanced. First, check the number of zinc atoms. There's 4 zinc atoms, there's 4 zinc atoms. Second, check the number of nitrogen atoms. There's 2 N's, there's 2 N's. Okay? Then, check the number of oxygens. I've got 6 over here, right? 3 times 2 is 6, plus 5 more. Okay? So that's 11, which is an interesting number. You don't usually get 11. And then over here, though, I've got 8 O's, and 3 more O's is 11. Last, check the hydrogens. 2 hydrogens here, plus 10 over here makes 12. How about over here? 4 and 8 make 12. Last thing, check the charge. The total charge on the left is 0. The total charge on the right is, I've got a 4 times plus 2 gives me plus 8, and that cancels with this 8 times minus 1. So this whole side is 0, this whole side is 0. They're not always 0 and 0. They could be a net charge on both sides, okay? Good. Okay, here's the third one. We're going to start to go a little faster as we get better at these. This one is done in base, so I'll do it in base first, and then if you wanted to switch it over to acid, you always can do that because you can neutralize the OHs with H pluses. Okay, so what's my first job always? Let me cover up. Okay, much better to turn the paper sideways. See how much more room I have? Okay, my first job is to figure out what's oxidized and what's reduced. So let's put down all the oxidation states. So first one, I minus, this oxidation state is obviously -1, monoatomic ion. Okay, manganese, we've seen this before. The whole thing is, permanganate, the whole thing is -1. So I get +7 for the manganese, again, because each oxygen is an oxide at -2. So 4 times -2 gives me -8. If this stuff is -8, this guy's got to be +7, so the whole thing equals -1. Okay. Over here, what's the iodine in this iodate? Well, the charge on the ion is -1, so oxygen is in its usual oxidation state of -2. So these 3 oxygens will give you -6. So the iodine has to be +5 because +5 and -6 equals -1. Okay, how about manganese dioxide or manganese Roman numeral 4 oxide? Oxygen is in its usual oxidation state of -2. Nothing's happening in terms of oxidation and reduction to oxygen. Oxygen is going to always be -2. That's what you're going to have. All these oxy ions, all of the things like nitric acid, sulfuric acid, all the oxygens are just going to be always -2. So if these oxygens are both at -2, that gives me a -4. So the manganese has to be +4. All right, so iodine is going from -1 to +5. Wow, that thing is doing what? It is giving off electrons like crazy, right? It's got 1 extra, and then all of a sudden it's down by 5. So that's an oxidation. So iodine is being oxidized, okay? And manganese is going from +7 to +4. So its number is reduced. Look at that. That's what reduction is, the reduction in the number. So from +7 to +4, that's capturing 3 electrons. So this guy's reduced, this guy's oxidized. Okay, again, doesn't matter which one you put on the left and which one you put on the right. I tend to put the oxidation on the left because I think of it as the quarterback. It's throwing the passes. So I put that first, and this is the receivers. They're catching. So R is like receiver, right? They're catching the electrons. Okay, again, first thing you do, just write out the 2 parts. Okay, you don't have any electrons yet over here. You just have those 2 things. This goes to this. So the very first step is balance the number of non-oxygen hydrogen atoms. So there's 1 iodine here, there's 1 iodine here, leave it alone. Next step, put in the electrons that account for the fact that the one iodine went from -1 to plus, guys, this should be +5 over here, not -5, to +5. So how do I go from -1 to +5? I need to add 6 electrons. That iodine lost 6 electrons. Don't worry about the charges yet. That's going to come later. Okay? At this step, I'm just adding the correct number of electrons to account for the fact that the only iodide went from -1 to +5. Okay, now the next step is balance the charge. So forget about the oxidation states the rest of the way. Erase them, take them off. They're only going to get you confused. Now I'm adding what? I'm going to add, since this is in basic solution, I'm going to add hydroxides to the more positive side so that the charges are equal. Okay, so this side is -1. This side is what? -7, right? So I need 6 hydroxides over here so that this whole side is equal to -7 and this whole side is equal to -7. After I add the 6 hydroxides, I need to add water to the other side. Don't worry about the O's, count up the H's. I have 6 H's over here, and that will drive how many waters go on the other side. So when you're doing it in base, you're working with hydroxide, and you're going to work with, and I'm not saying it's going to be on the left or the right, you don't know. You're putting the hydroxides on the more positive side so that you get it equal. Okay, so now these are -7 is equal to -7. Next, put water on the other side to balance out the H's. So I'm going to need 3 waters because I have 6 hydroxides. You always need half as many waters as the hydroxides. Good, so there's my 3. All right, at this point, the oxygens should have fixed themselves. 6 O's, 3 O's, and 3 O's. This is a totally balanced, beautiful half reaction like you would see in a book. Okay, it's got all of the elements. I leave it right now. Don't touch it. Don't get distracted. Go over to the other side. So I'm going to cover it up. We'll get back to it. Now we need to work on the reduction side. Okay, what's happening? My manganese is changing from +7 to +4. Okay, before I put this, first thing I do, check that I have the same number of manganeses on both sides. I have 1, I have 1. Okay, now, why 3 electrons? This is a 3 electron reduction because how do I get from +7 to +4? I get there by adding 3 electrons. Once you get to this step and you have the correct number of electrons, forget these numbers on the top. They're only going to confuse you. The rest of the way, you're only dealing with the overall charge and the number of atoms. Okay. Next step, you need to add hydroxides to the more positive side so that the charges balance. Okay. So let's see how many I should have. I have a -4 over here and a 0 over here, right? So I'm going to need 4 hydroxides on this side so that -4 equals -4. Okay, and that's what I did. Right? That's the motivation for those 4. Next step, I just added some H's to here. I need to put the same number of H's on the other side in the form of water. Well, I'm always going to need half as many, right? So this is 4 hydroxides. I'm going to need 2 waters on the other side. There's my 2 waters. Okay? When I get to this point, it should be the hydrogens are balanced, the charges are balanced, and the oxygens should have fixed themselves. So let's count up the total oxygens on the left. I've got 2 here and 4 here, that's 6. I've got 2 here and 4 here, that's 6. The total charge over here is -4. The total charge over here was -4. We know that should be okay because we already fixed that. That was our motivation for adding these 4 hydroxides to get the charges equal. Now I have a 3 electron reduction and I have to put it together with a 6 electron oxidation. So I'm going to leave this one alone and just rewrite it at the bottom, but I have to multiply this by 3. Why? Because the electrons that are lost have to be captured by the same guy. So this guy has to be multiplied by 2. Okay, so multiply that one by 2, multiply by 2, multiply by 2, multiply by 2, times 2, times 2. Put them together. The put them together part, I rewrite them one on top of the other. It doesn't matter which one's first. And I cancel everything out. The electrons have to cancel, right? These are 6, this is a quarterback throwing 6 passes. Here's receivers catching the 6 passes, right? This one quarterback throws all 6 passes, okay? Then he's got 2 receivers catching 3 each. So he's got 2 superstars, okay? That's pretty cool. Good. I'm trying to think of a team with 2 great receivers like that. Way back when, a long time ago, Pittsburgh Steelers had Terry Bradshaw was a quarterback, and he had John Stallworth and Len Swan. So he had 2 fantastic receivers. Usually teams have 1 fantastic receiver and a couple of other good ones, okay? But Pittsburgh Steelers had 2 great ones, okay? If somebody was there to complement Jerry Rice, then there would have been 2 great receivers in San Francisco. But I think he was pretty much by far the best receiver on his team, okay? Good. Okay, what else cancels? These 6 hydroxides cancel with 6 out of the 8 of these hydroxides, so there's only 2 left. These 3 waters cancel with 3 out of the 4 waters over here, so there's only 1 water left. So when you have oxy ions on both of them, you're going to get a whole lot of stuff to cancel out. You're going to get hydroxides and waters to cancel out. Okay? All right, when you're done, all the elements have to be balanced. The total charge on the left has to be balanced with the total charge on the right. So let's do that. -1 and 2 times the -1. This is -2, and a -1 makes -3. -1 and 2 times -1 equals -3. Okay? This guy is done. I won't go through each individual element. That's what you're looking for, and it was done in base because you have waters and hydroxides as your extra pieces. In acids, you'll have H pluses and waters as your extra pieces. Okay, I have 1, 2 more, okay? I think what I'll do is I'll go through just the first one to keep this to a shorter video, and then the second one you guys can work on your own, and let me know if you have any difficulty, okay? So this one is also done in base, okay? So you get everything that's written up at the top here. Get myself a nice fresh piece of paper. You get all of that stuff, and it says in base. So first thing you do is you need to mark up the atoms that have undergone oxidation and reduction. So this is called dichromate ion. It has a -2 overall charge. We know our oxygens, guys, are always -2. This is oxide, this is oxide. These guys are going to be -2 in carbon dioxide. Oxide everything. Oxygens are -2. So 7 oxygens at -2 gives me a -14 charge. So both of these chromes have to carry a +12 because +12 and -14 equals +2. So each chrome is +6. So you guys can't see that, but that's the oxidation state on chrome. It's +6. Okay, let me see if I can write it a little better. Okay, that's a little better, right? And let me get my plus sign better. Okay, so that was your job to figure that out. Okay, what about the carbon over here? What's happened to it? So, let's see what chrome did on this side. Well, this is just chromium ions in the +3 state. So monoatomic ion, the charge is +3. Okay. So what's happening to chrome? Chrome is being reduced, right? Look at it, right? Chrome is going, each chrome now is +6, so they're going to have to multiply this by 2. Each chrome is gaining 3 electrons, so this is going to be a 6-electron reduction, okay? Let's see what happened to carbon. There's 2, this is called oxalate, okay? You know OxyClean that they sell? Well, this is the cleaning agent. It's oxalate. So what's going to happen to oxalate? Well, we're going to see, well, this is reduced, so oxalate is probably going to get oxidized. But let's see. So oxalate is -2 is the overall charge on the polyatomic ion. Each oxygen is always -2. So this is going to give us a total of -8 for the oxygens. So all the oxygens equal -8. So these 2 carbons together have to be +6. Where do I get that from? +6 and -8 equals -2. So these 2 guys together are +6. So what's each one? +3. Okay, those two carbons here are going to go to carbon dioxide. So we'll take care of the fact that I need to double the carbon dioxide in a minute. But let's see what happens. Carbons are going from the +3 state to the +4 state in carbon dioxide because oxygen is always -2. Times 2 gives you -4. Carbon dioxide has no charge. So this carbon is going to be, has to be in the +4 state, right? +4 and balance is 2 times -2. So this is a 1 electron oxidation, okay? But it's going to happen twice. So it's going to turn out to be 2, right? Because I'm going to have to double this. And I'm going to have to double this, right? So let's see when we write them down. So this time I wrote the oxidation. Well, I think I've been consistent, right? I wrote the oxidation on the left and the reduction on the right. First thing, balance the atoms that are other than oxygen and hydrogen. So there's 2 carbons here. I've got to quickly double the carbon dioxide, right? Because you have to have, can't lose carbons. So after I do that, then I take care of the oxidation state. Each of those carbons is in the +3 state over here. Here, each one is in the +4 state. So if each one loses 1 electron, that's a total of 2 electrons that are lost. So these 2 electrons are here because the 2 carbons are going from +3 to +4. Okay. Next step, right? The next step is I need to add, this one is in base again, okay? So I need to add hydroxides to the more positive side, okay? So at this point, you forget about all the oxidation states, and all you care about is the overall charge. This side is -2. This side is -2. Oh, leave it alone, right? I've got everything good. I don't need any hydrogens in here. This guy turns out to be totally balanced. Let's check it out. First, is the overall charge balanced? Yes, this is -2. This whole side is -2. So you're only going to add OHs when the charges don't naturally balance. This one naturally balances. So oxalate's big reaction is to turn into carbon dioxide, so it makes bubbling when you're cleaning with your OxyClean, and it donates 2 electrons. And those 2 electrons kill microorganisms and make your clothes white. So this oxidation reduces something else. Okay. In this case, what's it reducing? It's reducing the dichromate. So first step, there's 2 chromes here, so I'd have to double this, right? Up here, there's only 1, right? So they can't have that. So double the chrome, because the first thing I do is take care of any elements other than hydrogen and oxygen. Next, I've got 2 chromes, each at +6, right? And they're going to +3. So each one, how do I get from +6 to +3? This is +6. Sorry, these are so small. How do I get from +6 to +3? Each one needs to gain 3 electrons. But that's happening twice. It's happening to the first guy and then the second guy. So this is a 6 electron reduction. Okay? So at this step, adding this 6 electron is just to take care of the fact that the chrome went from +6, 2 chromes went from +6 to 2 chromes at +3. Next step, forget the oxidation states. Just take care of, so the only thing I have to forget now is this. Take care of the overall charges. Since I'm in base, I use hydroxide. Add hydroxides to the more positive side so that the charges are balanced. Okay, this is -6 and a -2 is -8. This is +6, right? Wow. So this is -8 on this side. I'm going to need a lot of hydroxides. This guy is +6. Okay, I've got to add 6 hydroxides, right, to get this to 0. And then another 8 after that to take care of that -8. I'm going to need 14 H pluses. Holy cow. I don't know if I know of any other one that I'm going to need to put so many H pluses. And there they are. There's my 14 H pluses. When I get to this point, okay, my total charge should be balanced. +6 and -14, right? +6 and -14 gives you a -8. Okay? Excuse me, let me make sure I got that right. Let me get a different piece of paper so I don't cover up the wrong thing. Okay? So this is, right, plus 6 over here, right? And negative 14, right? Sorry, I'm spazzing out. My screen went off. Just hang on one second. Gives me a negative 8. Sorry about that. Okay, so I got negative 8 over here. Then, right, so that's right. So this is going to be giving me, my chrome is at negative 2. Oh, I'm okay. This guy looked like a positive. Sorry about that. This is negative 2. Okay. So negative 2 on the chrome 8 plus 6 electrons will also give me negative 8. So my charges balance out. Good. I thought I got it wrong. Okay, last step. The last step is, oh, let me cover this up. I need to add waters to the other side so that the H's are balanced. So if I have 14 over here, there's no other H's, so I'm going to need 7 waters, because 7 times H2 will give me 14 H pluses. Okay. Now, if you've balanced the H's and you've balanced the charge and you did everything right, the oxygens should fix themselves. I've got 7 O's here plus another 7 here. There's my 14 O's. So the oxygens totally balance each other. Okay, so now I put them together. This is a 6 electron oxidation. This is a 6 electron reduction. Just coincidence. There's nothing to multiply by. I've got these guys throwing 6 passes. That's, I think, of the footballs, right? And these are 6 receivers catching the passes. So put them together, rewrite this one, rewrite that one. Okay, there's going to be stuff that cancels. First thing that cancels, the electrons, right? So the electrons have to cancel, otherwise you did it wrong. So 6 here cancels with 6 here. I don't know if I see anything else that cancels. Okay, the reason why nothing else cancels is I didn't have to do anything to this side. I didn't have to add OHs. I'll get stuff, other things than electrons to cancel out when I have to add H pluses or OHs. So the electrons cancel out, nothing else cancels. I get 7 waters, 1 dichromate, 3 oxalates, go to 6 carbon dioxides, 2 chromes, and 14 hydroxides. Okay, not going to redo the mass balance, but if you got the charge balance right, you probably got the overall thing right. So in any chemical reaction, the total charge on the left-hand side has to equal to the total charge on the right-hand side. So this is uncharged. This is minus 2. This is minus 6, because 3 times minus 2 is minus 6. So I get a total of minus 8. On this side, no charge. This is minus 14, and this is plus 6. So minus 14 and a plus 6 gives me a minus 8. Over here, since I have it already, here's what's happening with the oxygens. I should have 26 total oxygens over here, and then over here I should have 26 total oxygens. So check everything else will be okay. We went this far, might as well do everything else. Here's my only hydrogens are in water, so there's 14. Only hydrogens are in hydroxide in this case. There's 14. 2 chromes, chrome times 2. 6 carbons, 3 times 2. 6 carbons, 6 times 1. Okay, so that one is completely done. Okay, here's the last one. What the heck? Might as well just go ahead and do it for you. Okay, do it with you. Okay, so you try it on your own. So this is an interesting one because this is what we had talked about in the beginning of the last chapter. This is a disproportionation. I have, this is chloric acid, right? I have chloric acid, and the chloric acid, you're going to have 2 of them, right? Because one of them is going to get oxidized and the other one is going to get reduced. So I give you this and I'm telling you it's an acid. Okay, so the first thing that we're going to have to do is we're going to have to double this, because right up here, because how can I have 1 chlorine go to 2 chlorines? So I could double this and think about it as I've got one of these, that's going to transition to this, and the other ones that's going to transition to this. So let's do the oxidation one first. This is the chlorine in the +5 state. Why? Hydrogen's +1, oxygen is -2. This is all -6 over here, and this is +1 over here, so chlorine's got to be in the +5 state. So in the chloric acid, chlorine is always in the +5 state. Okay. When it gets oxidized to perchloric acid, it goes to the +7 state. Again, because oxygen is always -2, this gives you -8. This is +1, so that guy has to be +7. So the oxidation is chloric acid going to perchloric acid, and I wrote that over here. Okay, so that's all I have so far. The reduction is, again, I probably should have just rewrote another one of these because you're going to take two of these. You can't split and make two. So I have another chloric acid in the +5 state, and it's going to go to chlorine dioxide, okay, which is in the +4 state. Why +4? This whole thing is equal to 0, and oxygen is always -2. I would do this whole chapter, think about oxygen as oxygen in the -2. The only time you're going to see oxygen not in the -2 is when it's oxygen molecules, okay? I won't give you a peroxide question. So this is chlorine in the +4. So that's the reduction. It's going to be chloric acid going to chlorine dioxide over here. Okay, so let's not get confused. Let's cover this up and do our job. Okay, so first job is identify the oxidation states. This guy we said was in the +5 state. This guy's in the +7 state. So this is pretty easy to see now because this is just a one chlorine here, one chlorine here. How do I get from +5 to +7? The only way to do that is to lose 2 electrons. After I lose 2 electrons, this is an acidic solution, so I need to add hydrogen ions to the more negative side. Well, this right-hand side is more negative. This has no charge, right? Forget the oxidation states once you add the electrons. Please forget the oxidation states once you add the electrons. Okay, so how many hydrogens do I need? This has no charge. This is -2, so I'm going to need 2 hydrogens here. And then the last step, add, if I need them, okay, might not need them, add waters to the other side to balance the H's that I just added. I have 1 H here, I have 1 H here, and I have 2 H's here, so I have 3 H's, but one is taken care of. So I'm going to need 1 water molecule on this side, right? Because I'm missing 2 H's. So there's my 1 water molecule. That's the only thing I added from here to here. So charge before mass method, add the electrons first, then add H plus as an acid, then add water to the other side. This is totally balanced, charge balance and mass balance, right? This has no charge. This is +2 and -2, cancel out. 1 chlorine, 1 chlorine. 3 H's, 3 H's, 4 O's, 4 O's. Okay, let's do the other one. Here's the reduction. Forget that for a while. Go over to the other side. On this side, remember, I have to go from here to here. This has chlorine in the +5 state going to chlorine in the +4 state. That's a 1 electron reduction. The number got reduced from 5 to 4. So I have to capture 1 electron. Okay, so this guy's catching 1 pass, whereas this guy was throwing 2 passes. So 2 receivers are going to have to pick up the ball, right? This is throwing 2 at the same time. This is going to do 1 at a time. Okay, don't worry about that. Right, so after I add my electron, what's my next job? I need to add H's to the more negative side. So that's going to be on this side. Remember, forget the oxidation states, those little numbers on the top. Just go with the overall charge. Well, this has no charge, right? This acid has no charge. There's 1 electron, so I'm just going to need 1 H plus over here. Just going to put 1 H plus over here, okay? Because +1, -1, and 0 will equal 0. So I'm adding H pluses for the overall charge. Forget the oxidation states. That's what I did. I added my 1 H plus. Now, I lucked out. Okay, here's 1 H. Here's 1 H on this side. Don't have any H's on the other side, so I'm going to have to add 1 water on the other side. There it is. Okay, after I do that, the oxygen should have taken care of themselves. Here's 3 oxygens. Here's 2 oxygens and 1 oxygen. Okay, next thing, check the charge balance. Charge balance, this charge balance again is 0 equals 0, 1 chlorine, 1 chlorine, 3 oxygens, 3 oxygens, 2 H's, 2 H's. Okay, I have a 2 electron oxidation and a 1 electron reduction. Take the reduction, multiply it through by 2, then put them together. Okay, this guy got multiplied by 2 and came down here. This guy just got rewritten. Okay, put that like that. Let me make it a little smaller. This guy just got rewritten. This one got multiplied by 2 and put down here. Why multiply by 2? Electrons always cancel out in oxidation reduction. You can't just send the electrons off to midair. They have to go someplace. They can't have a quarterback throwing passes without a receiver catching them. Oxidation is always accompanied by reduction. Okay, let's cancel the electrons. 2 electrons, 2 electrons. Now, both of these involved oxyions. So there's going to be a whole lot of extra H pluses and waters. Okay, so let's see. I got a 1 water over here. I've got 2 waters over here. So this one cancels and this one 1 out of the 2 cancel, and I have 1 left. Okay. All right. What about H pluses? Here's 2 H pluses on this side. Here's 2 H pluses on this side, so they totally cancel out. So what's left here? This is really neat. I've got 2 chloric acids here and 1 chloric acid there, so they actually add up. They don't cancel out. 1 plus 2 makes 3 chloric acids. So 3 chloric acids disproportionate, right? 2 of them undergo a reduction and 1 of them undergoes an oxidation. So they all kind of smash together in a way. They're not going to all smash together at exactly the same time, but ultimately 3 of them get together, 2 of them oxidize, 1 of them reduces. I get perchloric acid. So this is the more oxidized version. You could tell it's got 4 oxygens, right? So along with the fact that oxidation is the loss of electrons, what you're going to learn in organic chemistry is a lot of times you become more oxidized. You actually get more oxygens on you, and that's what happened here. Okay? And total charge, 0 equals 0, so that always has to happen. Count up all of the elements. Here's 3 chlorines. Here's 1 chlorine plus 2 chlorines is 3. Here's 3 H's. Here's 3 H's, 2 and 1. And then here's 3 times 3 is 9 O's. Here's 4 O's plus 4 O's. That's 8. Plus 1 more makes 9. So there's my 9 O's. So this is totally balanced. And that's everything for me teaching you how to balance oxidation reduction reactions in either acidic solution or basic solution. See you next time, guys.